Cassandra was on. Good both there, right? Kelly told me that Cassandra was going to be downstairs. Okay. It's redirected, sounds okay. Well, I mean, they should be doing
It's
it.
kind of complicated, but there are like a few places that do proximity based, so you're not under pressure all the time. But then finding housing is near impossible, and the prices are just insane. And it's like, you're a super far from campus, you wouldn't be using of that. Is this even worth it for acquiring things? Your post office
All right, the suspense is killing me. I think we should get started. It's my great pleasure to introduce Salar Fattahi from University of Michigan. Salar finished his Ph.D. at University of California, Berkeley, 2020. If you read his CV, you'll see he already has quite an impressive academic record with no fewer than 20 awards. Maybe the two most impressive being an NSF Career Award and an Informs JFAG second prize. But that's still quite an amazing accomplishment for that award. He started, I think, his career doing his early work was mostly for optimization involving power systems, so applications of energy and power systems. And lately he's shifted a little bit, even though those were non-convex problems, but he really is focusing more on the methodology of non-convex optimization more generally. And I think that's what he's going to share with us a little bit today about this very interesting title about finding the needle in the haystack. So please join me in welcoming Salar.
Thanks, Jeff, for a very kind introduction. Yeah, I'm going to talk about gradient descent and how it converges sometimes to low-dimensional solutions in over-parameterized models. This is I would say the majority of this work is joint work with two of my now former PhD students, Jianhao Ma, who is doing his postdoc at Penn, and then he's going to become a tenure-track professor at Tsinghua University. He promised me that he's going to send a lot of students to us. And then also Gay Young, who's an applied scientist at Amazon and is making a lot of money. All right, so I'm sure I don't need to convince this crowd that modern optimization problems, especially those arising in machine learning, are becoming increasingly non-convex and increasingly massive scale. These problems typically range from simple classification tasks all the way to generative AI, maybe genomics, and even safety critical applications such as autonomous driving. So in all of these problems, there is an optimization problem to be solved. We typically try to fit a highly nonlinear model, say a deep neural network, to a bunch of samples. Some of those samples could be corrupted with noise. The underlying non-linearity in the model actually gives rise to non-convexity in the optimization problem. Okay? So now, motivated by this, the ultimate goal of my research is to design and analyze efficient and sometimes guaranteed algorithms for non-convex and larger scale problems, especially in machine learning. And to do that, over the years, my colleagues, students, and I, we worked on three, I would say, main classes of optimization: smooth and non-convex, non-smooth and non-convex, and mixed integer and non-convex. The main part of my talk will be devoted to smooth and non-convex. I will briefly allude to non-smooth and non-convex, and unfortunately I will not have time to talk about mixed integer and non-convex. Apologies to the experts in the room. But I do want to mention that this doesn't mean that these problems are any less important. We actually do have some very recent, interesting results and applications in genomics in collaboration with USC and Michigan Medicine. I'm happy to discuss them offline. Okay? Okay, so what is the main workhorse behind solving optimization problems in machine learning? Gradient descent, right? You want to move towards the negative of the gradient until you cannot make any further improvement. You might argue that this version of gradient descent is rarely being used in practice. Sometimes, for example, you have non-smoothness, so you replace this gradient with an element of the subdifferential. Sometimes you don't want to compute the full gradient, you replace it with a stochastic variant of that. And sometimes you want to be fancy, speed things up, you add preconditioning, right? So in any case, you could argue that you either use gradient descent or a variant of gradient descent, right? So now this leads to another question: does gradient descent algorithm actually work? Does it actually minimize the function that you want to minimize? Now, depending on who you ask, will make a different answers to this question. So if you're sitting on the theoretical side, you would probably say that non-convex problems are difficult in their worst case, and gradient descent actually in many cases can get stuck at bad or suboptimal local solutions, right? And in many cases, we don't have an efficient way to distinguish between local versus global. If you're sitting on the practical side, you would probably say training non-linear neural network is easy, just use SGD, right? So $1 million question is, why is there a gap? Why do we keep using gradient descent and its variance, despite the fact that we know in their worst case, they may actually fail, right? So to answer this question, we need to go one step back and see why we like gradient descent in the first place. One good thing about gradient descent, as we all know, is that if you apply it to convex functions, it is guaranteed to converge to the globally optimal solution under some conditions. The bad news is most of the problems in machine learning, they're non-convex, so your gradient descent algorithm may get stuck at a bad local minimum. Now, despite this, in practice, as I said, we use gradient descent algorithm all the time. It's the main algorithm for training neural networks. And they actually, in many cases, they actually work pretty well, right? Now, this observation very recently gave rise to this new paradigm in optimization, which is called benign landscape, or problems that are free or devoid of suboptimal local mins. Basically, all local minima are equally good. This is one example. All these solutions, they're at the same level. Why do we like benign landscape? Well, because with benign landscape, variants of gradient descent provably converge to global solutions. Okay? But I mean, this raises another question: do we have benign landscape in machine learning? Right? In recent years, I would say a number of breakthrough results actually showed that many classes in non-convex optimization problems in machine learning, for example, low-rank matrix recovery, dictionary learning, phase retrieval, even some classes of neural networks, they do have benign landscape. Now, this result, or results similar to this, actually are very, very useful, very impressive, because they actually help us to move away from arguments only based on convexity versus non-convexity. But if you dig deeper, you'll see that they actually rely on a bunch of assumptions. For example, they assume that the model is exactly parameterized. What does that mean? It means that I know exactly how many parameters I need in my model. They also, in many cases, assume that the loss function is smooth, or the data is almost noiseless. In reality, however, none of these conditions are satisfied. For example, in many cases, we don't know the model. That's why we're solving this optimization problem. We don't know the model, so we don't know how many parameters we need in the model. So we over-parameterize or overestimate the number of parameters just to be safe. Okay? Okay, I will give you a few examples of this later, right? Also, in many cases, the loss function is non-smooth. Sometimes it's very non-smooth. This is a landscape of a realistic neural network. You can see that it has a lot of kinks. And sometimes the data is noisy. Sometimes it's noise, could be outlier noise, could be adversarial noise. So a follow-up question is, can we relax these conditions? Can we guarantee benign landscape in the face of over-parameterization, non-smoothness, and noisy samples? Okay, so if I wanted to summarize our key contributions in 2 key bullet points, it would be these. First, as soon as you over-parameterize, you lose benign landscape. As soon as you overestimate the number of parameters, you lose benign landscape, which kind of makes sense, right? Because even if you overestimate the number of parameters, your model has too much flexibility, so you have the capacity to overfit to noise, right? So you may have undesirable solutions. The second takeaway message is that actually, despite this over-parameterization, gradient descent can be provably agnostic to it and converge to low-dimensional solutions. Now, if you want to stop listening to my talk, this would be the ideal place, because for the rest of my talk, I will try to clarify these 2 points. Okay? So I would say the main part of my talk will be focused on over-parameterized models. I'm going to assume smoothness, and I'm going to assume clean data. This part is based on these 3 papers. The majority of the things that I'm going to talk about is based on this recent paper with my students. I do want to mention in passing that we do have extensions to non-smooth, loss, and noisy data. I will briefly allude to them towards the end of the talk if I have time. Okay? Now, here's the outline of my talk. First, through some examples, I will explain what I mean by over-parameterization and implicit regularization. Then I'm going to talk about our general theory, and then I'm going to take this general theory and apply it back to the examples I mentioned. Okay? All right, so the first example is related to this classical sparse recovery problem. Given a bunch of samples, xi's and yi's, my goal is to find a sparse vector theta star with at most k non-zero elements, whose inner product with xi would give me yi. Okay, it's a classical problem. Now, a critical and I would say very realistic assumption is that we typically don't know this sparsity parameter k. We don't know the number of non-zeros, right? What is the typical way of solving this problem? We regularize the sparsity, right? We just try to minimize the sum of squares plus this regularizer that has a role of promoting the sparsity. For example, if this is L0 penalty, it's one choice. If you use L1 penalty, that's lasso. That's classical lasso problem, right? But this leads to another question. What value should we pick for lambda, right? This regularization coefficient. Now, turns out the statistically optimal choice for lambda actually does depend on this theta star, which you don't know, and specifically the k, right? So how do we go around this issue? How do we handle this in practice? We do, for example, cross-validation. We try a bunch of values for lambda, pick the best one, right? Now, a recent paper, this paper, suggested an alternative approach for solving this problem, which I find quite interesting. They suggest to first model this theta star as the entry-wise product, or Hadamard product of 2 vectors, same size, so theta I would be equal to ui times vi, right? And then run gradient descent with small initialization directly on this sum of squares loss with no regularization whatsoever, okay? Here's the performance of the alpha, gradient descent, right? This blue curve is the distance between our model and the true k-sparse solution, which goes down all the way to 10 to the minus 10. This red curve, I will talk about that later. But based on this, I can make 2 observations. First, the dimension of the optimization problem is unnecessarily large. Here, I have 2 vectors that I need to optimize. Each have length d. So in total, I have 2 d variables. The inherent dimension of the problem is k, because if I knew the sparsity pattern, I could just restrict my optimization problem to the support, which has k elements. This is what I mean by over-parameterization in this context. We have more variables than we need. Second observation is this implicit regularization. Seems like gradient descent with small initialization does converge to this k-sparse solution. Now this is what I find surprising, because there's no reason for your gradient descent, no direct reason for your gradient descent to converge to a sparse solution, because you're not promoting sparsity, at least explicitly. I'm not adding any kind of penalty in the objective. I'm just minimizing the sum of squares. But it seems like gradient descent does have this implicit regularization phenomenon by itself, and it does converge to a sparse solution. Okay, this is one example. Second example is related to this famous low-rank matrix recovery. Given a bunch of samples, again, xi and yi, our goal is to find a rank R positive semi-definite matrix M star, whose inner product with xi would give us yi. Right? It's like a matrix version of the sparse recovery problem. For the experts in the audience, special cases, matrix sensing, matrix completion, which has many applications, for example, in recommendation systems. Right? Again, a critical assumption and a realistic assumption is that this rank R is typically unknown. We don't know the rank R. The classical way of solving this problem is based on convex relaxation. We trace regularizer that again has the role of promoting the low rankness in the solution. But in addition to the type of problems that you would face in the sparse recovery, beyond that, this problem essentially boils down to a semi-definite program. And you don't want to solve semi-definite program in large scale, right? And so a series of recent papers, again, suggested let's model this M star as UU transpose. U is a D by D matrix, okay? This form, UU transpose, already imposes the Ph.D.ness, positive semi-definiteness. And again, just run gradient descent with small initialization on this, again, sum squares loss, with no regularization whatsoever, okay? Again, this is the performance of the algorithm. Again, this is the error that goes down to 10 to the minus 9. I can make similar observation. First, the problem is over-parameterized. Why is it over-parameterized? The dimension of the matrix variable is d by d, right? That's the dimension of U. If I knew the rank R, I could essentially restrict the number of columns in U to R, because that would impose rank R constraint, right? So the optimization problem has dimension d squared. The number of the inherent dimension of the problem is d times R. And sometimes R can be significantly smaller than d. Also, we have implicit regularization because, again, gradient descent with small initialization does converge to a rank R solution. Okay? You might argue that, okay, these two examples are synthetic. Do we see implicit regularization over parameterization in realistic settings? My third example is on realistic neural networks. Here, what I'm showing you is a trajectory of different gradient-based algorithms, for example, Larson and Adam, on different neural network architectures, okay? To visualize these trajectories, what we did was we took the trajectory of the algorithm and we projected it onto a randomly generated orthonormal basis. What you're seeing here is the top 5 coefficients of that projection. Okay, so we take the trajectory, we project it onto an orthonormal basis, we sort the coefficients. What I'm showing you is the top 5. Now, I can make a few observations based on this. First of all, there's no observation to be made. Everything, it seems like there's no clear pattern, and in fact, the energy of the signal is spread out. Energy of these coefficients is spread out. Here, I'm only showing you the top 5 coefficients. If I were to show you top 100, you would see that they're all around the same range. You could argue that, well, you don't see any pattern because you're not learning anything. What are you converging to? That's not at all the case. These are highly tuned algorithms that achieve 90% accuracy on realistic data sets. So a natural question is, where is over-parameterization? Where is implicit regularization? Right? Now, it turns out, if I use a different orthonormal basis, things would look much nicer. Now, here what I'm showing you is exactly the same trajectory, but now projected onto another carefully designed orthonormal basis. Okay? I'm not going to tell you what this orthonormal basis is. If you're interested, you can take a look at our iClear paper, and I'm happy to discuss it offline. But you can already see that things look much nicer. Things are more monotone. And in fact, these coefficients are no longer spread out. I don't think you can see, but here the scale is 100 times larger than here. So the magnitude of these coefficients are 100 times larger than this. And in fact, if I plot the distribution of these coefficients, you would see that the top 10% of these coefficients actually carry 95% of the energy. Okay, this is where the low dimensionality emerges. Because again, it seems like gradient descent does converge to a low dimensional solution or sparse solution, approximately sparse solution, after this change of basis. Okay? So I hope I could convince you that both implicit regularization and over-parameterization, they're prevalent in machine learning. So our goal will be to see if we can find a unified way of studying them. Any questions? Yeah.
So after you called me out, now I have to return the favor. But, so what's interesting about this last example, so you're saying it doesn't matter if I'm doing atom or I'm doing momentum, all the other stuff around the gradient descent, they all exhibit the same kind of behavior.
So Lars, Adam, yes.
So the only thing that's
SGD
important is the gradient descent part, basically.
Yeah, so of course the result, everything I'm going to talk about, I'm showing you all these nice experiments. All of our theoretical results will be on gradient descent,
Right.
not even stochastic gradient descent. But this is, the reason why we're looking at these kinds of experiments is because we do see this phenomenon, not only on gradient descent, but also SGD, also Lars, also momentum-based algorithms. Yeah. Any other questions? All right. So a recurring theme of all of these problems is that we want to essentially minimize a function from Rd, let's say, to R by directly running gradient descent. Here, I'm going to make two assumptions. First, I'm going to assume that this F is both gradient and Hessian-Lipschitz. It has some level of smoothness, but potentially non-convex. And the second assumption I'm going to make is that I'm going to assume that F has a potentially unknown implicit region M. I'm going to show it with M, with dimension K, and K is significantly smaller than the dimension of the problem. Now, the full characterization of this implicit region M is unknown to us, but it does contain the low-dimensional solution that we want to converge to. Let me give you a few examples. In sparse recovery, remember the way we modeled theta was the entry-wise product of U and V. So one choice of this implicit region is a set of all U and V such that Ui and Vi is 0 whenever theta star I is 0. Basically, the sparsity pattern of U and V matches the sparsity pattern of theta star. Now, obviously, I don't know theta star, so I don't know this implicit region before solving the problem. Here is a second example, low-rank matrix recovery. Again, remember, we model it as UU transpose, right? U is D by D matrix. So one choice of this implicit region would be the set of all U's whose rank is at most R. Again, I don't know R, so I don't know this implicit region before solving the problem. Despite that fact, gradient descent does converge to a solution that is approximately in this set. And for deep neural networks, you can define this implicit region as a set of all weights such that these weights have k non-zero coefficients after an orthonormal basis. This is even more complex. We don't know k, we don't even know the orthonormal basis, which orthonormal basis we should use before solving the problem. Okay, so what is our goal? Our goal is to identify conditions under which gradient descent converges to a local or global minimum of this function f within this implicit region M. That's the goal, because that's what we see in practice, right? Gradient descent does converge to a solution within this M. Now, I need to clarify one thing. Is this a reasonable assumption? Can I guarantee convergence to local or global minimum? Not necessarily in the worst case, right? But turns out for generic functions, and this generic function has a precise definition. For generic functions, local minima are actually second-order stationary points of your function. Okay, so a more accessible goal would be to identify conditions under which gradient descent converges to a second-order stationary point. I'm going to show you the SOSP of this function f within this implicit region M. And I'm going to show these points as M SOSPs, the set of all points that are in M, and they satisfy first order and second order stationarity conditions. Right? We're almost there, except that I need to polish this a little bit more. First of all, we not only care about convergence, but also efficient convergence. And second, we can only guarantee convergence to an SOSP up to a certain tolerance, right? So if I make those changes, this would be the final goal. We want to identify conditions under which gradient descent converges efficiently to an approximate SOSP. And again, I'm going to define them as epsilon MSOSP. It's basically the same except that I need to satisfy these conditions up to an epsilon accuracy. So I need to make sure that X is close to M up to epsilon, and we satisfy first and second order stationarity conditions up to epsilon. Okay?
L is Lipschitz constant.
L is Lipschitz constant, and rho is the Hessian Lipschitz constant. Any questions about the setting? Okay. Now, if I want to guarantee my algorithm, any algorithm, converges to a point here, within this set, I need to guarantee two things. If I want to show gradient descent converges to an approximate MSOSP, I need to guarantee two things. One, I need to guarantee that gradient descent converges to an approximate SOSP, meaning that it satisfies first order and second order conditions, right? And second, I need to ensure that on top of that, we stay close to M, which we don't know. Again, this implicit region M, it's something that I don't know before solving. I'm just running gradient descent. Okay, so let's start with the first one, convergence to approximate SOSP. Now, a standard result by now for gradient descent in the non-convex setting is that it actually does converge to a first order stationary point efficiently. Now, about 10 years ago, this paper actually showed that gradient descent with the random initial point does converge to a second order stationary point almost shortly. Okay, so the only thing you need to do is to do random initialization. Now this is a very, very strong result, but the problem is that it may actually do so in exponential number of iterations. Okay? Now it turns out if you want to guarantee efficient convergence to second order stationary point, that's the goal, right? You need to resort to another variant of gradient descent, which is called perturbed gradient descent. So what is perturbed gradient descent? It's very similar to gradient descent except for one change, one minor change. When the gradient norm is large, you just take one iteration of gradient descent, that's normal, nothing new here. When the gradient norm is small, you first perturb your current iterate with a random perturbation that is drawn from a ball with radius gamma uniformly, and then run a fixed number of gradient updates starting from that perturbation. That's the key difference. That's where the perturbation is. Why do we do this? Why do we add this perturbation? Right? Why bother with that? Now it turns out if the gradient norm is small, you have only two possibilities for the point. You're either close to an approximate second order stationary point, as desired, or you're close to a strict saddle point. So intuitively, strict saddle point looks something like this. So this is a strict saddle. This is a first order stationary point, but it has a negative, strictly negative curvature along one direction. So ideally, you want to escape from this point, right? Because it's not a second order stationary point. Now, if I look at the gradient flow around this point, you can see that they look like this. Almost all of these flows, they eventually escape from this strict saddle point. They move towards the cold area, right? This is a negative curvature, right? Well, all of these flows, except for one, this one-dimensional, right? So if you're anywhere on this plane except for this one-dimensional line, you will eventually escape from strict saddle point. If you're on this line, you will get stuck. This should already tell you why gradient descent with random initialization is, you will not get stuck at a strict saddle point because the set of points from which you get stuck, they have measure 0. Right? So if you initialize randomly with probability 0, you will hit one of them. Right? Now, this raises another question. If gradient descent with random initialization, as we saw, will not get trapped at a strict saddle point, why do we need to add random initialization at these iterates? If random initialization is enough, why bother adding additional perturbations? I'm asking the crowd. Any idea?
If you're very close to that, it may take very small steps and slow convergence.
Exactly. Again, remember, we care about not only about escape, but also efficient escape. right? And if you want efficient escape, you essentially need to widen this band. So all the points in this red band, they will either get stuck at a strict saddle point, or they may eventually escape, but it will take them a long time to do that. All the points in this green region, they will escape efficiently. Now mathematically, I can actually define these regions. This red region is a set of all points from which gradient descent reduces the objective function by a fixed amount after a fixed number of iterations. Okay? And our stuck, this red region, is essentially the complement of that. Now the whole point of adding a large perturbation is that if the perturbation radius is large enough, you're more likely to land in this green region, because the volume of the green region is significantly larger than the volume of the red region. So even if you are in this red band, after one perturbation, you will, with high probability of course, you will land in this green region. In other words, the probability that this perturbed point is in this green, nice green region increases with the perturbation radius. Okay? Now this is the main idea behind this result from 2017, which basically says with high probability, perturbed gradient descent with perturbation radius that scales like this converges to an epsilon SOSP within this number of iterations. Okay, this is a very strong result, except that large perturbations can lead to large deviations from this implicit region M. Let me give you an example. This is the performance of perturbed gradient descent, the same algorithm that I talked about, on low-rank matrix recovery, right? So this blue curve is for the exact parameterization, meaning that I know exactly the rank of the true solution R. Okay, somebody gives me that rank, so I limit the number of columns in U to R. Right? This is the exact parameterization setting. Perturbed gradient descent does a very good job. It converges very fast at a linear rate. As soon as you overestimate the rank by 1, right? So this R prime is the number of columns in U. It's R plus 1. So I overestimate by 1, you can see that perturbation actually leads to a significant deviation from M star. Okay? Now to understand why this happens, let me go back to this example. Now let's say, again, for the sake of the argument, let's say my implicit region is this line, this yellowish line, which is a set of one sparse solutions. It's a set of all points where x1 is 0. Right? Now if I add a large perturbation, sure, I will escape from a strict saddle point, but at what cost? At the cost of potentially significantly deviating from this line as well. Right? So you can see that we have two opposing objectives here. On one hand, I want to have a large perturbation because I want to increase the escape probability, but that would lead to a larger deviation, as we saw. On the other hand, I want to have a small perturbation, small radius, but that could lead to a smaller escape probability. Right? So our key contribution here is actually small perturbation, small alpha, actually almost achieves the best of both worlds. What do I mean by that? If I want to guarantee efficient escape from strict saddle point, I actually don't need large perturbation. Small perturbation actually does that for us. Now, how do we show that? It seems a little bit counterintuitive. How do we show that small perturbation is enough for us to escape from strict saddle point, which is a good thing, right? Because I want to have a small perturbation because I don't want to deviate too much from this implicit region M. And to do that, what we did was essentially we characterized the width of this red region. And what we showed was you can actually shrink the width of this red band, you can shrink it, if you're willing to pay something in terms of the number of iterations. Specifically, what we showed was that you can shrink the width of this region by a factor gamma. Remember, gamma is the perturbation radius. If you increase the escape time, t, by a polylogarithmic factor. Now, what is the benefit of this? Why do we care about this? It basically says because this band is thinner, I can get away with a smaller perturbation, right? I can use a small perturbation and still with high probability, I can land within this green region. Okay? And this is the key idea behind this other slightly different algorithm, which we call IPGD, or infinitesimally perturbed gradient descent, which basically says with high probability this IPGD with arbitrarily small but positive radius actually converges to an epsilon SOSP within a number of iterations that is only polylogarithmically larger than perturbed gradient descent. Okay, so this is good because it says that perturbations do not lead to large deviation from this implicit region. But are we done yet? Not necessarily, because even if perturbations do not lead to large deviation, there is still a possibility for gradient updates to push you away, right? Even if you don't add perturbation, you're running gradient descent. So for example, if your iterations look like this, you have small deviation. If they look like this, you have large deviation, right? So our next goal is to characterize this deviation rate. And the way we do that is based on a single residual decomposition of each iterate. Basically what we do is that we take every iteration and we project it onto this implicit region M. That's the signal term. And the residual term is the orthogonal complement. Intuitively, it looks something like this. So these are the iterates. The projections, these points, these are the signal. The vector that connects them together, those are the residual terms. Now, I should mention that in practice, you don't need this. Right? This is only a tool for our analysis. In practice, you just run gradient descent. Right? But based on this decomposition, you can see that if I want to control the deviation rate, the distance between my iterates and this implicit region M, all I need to do is to control this residual norm, the distance between these two points. And that's exactly what we do. We show that if M is closed on the gradient updates, then this residual norm satisfies this bound. Now, before talking about this bound, I want to clarify one thing. What does it mean for M to be closed on the gradient updates? It means that if you start in M, you stay in M. Right? The next iterate of gradient descent stays in M. Again, the question must be asked. You don't know M. How do you guarantee this? Right? Turns out all of the examples that I mentioned, sparse recovery, low-rank matrix recovery, deep neural network, under some conditions, they do satisfy this closure property, which kind of makes sense. I mean, I will get back to that.
For the choice of M that you specify.
For that specific choice of M, exactly. So the choice of M really does matter. Of course, if I choose a different M, it may not be satisfied. Now, under this condition, what we show is that this residual norm satisfies this bound. What matters in the right-hand side is this quantity that I highlighted, which we call relative deviation. Now, the mathematical definition of this relative deviation rate is involved, but intuitively, roughly speaking, is the sum of two terms. The first term essentially measures the negative curvature of the Hessian along the residual that I defined. The second term measures the positive curvature of the Hessian along the residual. As I said, this exact definition does not matter. What matters is that this R of tau precisely controls the growth or the shrinkage rate of this residual norm. For example, if this deviation rate is positive, then this residual norm can grow. If it's negative, it will shrink. It will go down over time. For example, if your function is convex, you can show that this relative deviation rate is non-positive. If it's strongly convex, you can show that it's strictly negative. Right? So I mean, I have this bound that controls the residual norm, but it seems a little bit abstract. How tight is it? Does it really matter in practice what this relative deviation rate is? Turns out it does. It actually precisely controls this residual norm. I'm going to show it with some examples. Here what you see is the relative deviation rate. I show it with red, right? This is the relative deviation rate over different iterations. And across different over-parameterized models. For example, matrix factorization, matrix completion, one with matrix sensing, tensor factorization, sparse recovery. These are all over-parameterized models. This dashed blue line is the residual norm. Okay, so you can see if the relative deviation rate is large, this red part is large, you see a large growth, a fast growth in the residual norm. If it's small, for example, here it's small, residual norm really stays small. So it does precisely control the dynamics of the residual norm, which is again, like it affects the overall algorithm, overall performance of the algorithm. Now, putting everything together, we could show basically this result, putting this escape from strict saddle points and this residual norm dynamics. We could show that this algorithm, IPGD, infinitesimally perturbed gradient descent, which is very close to gradient descent. I would say much closer than perturbed gradient descent because the perturbations are very, very small. Does converge to an epsilon MSOSP under 3 conditions. The first one is closure on the gradient opposite, we already talked about. This is another strange condition. It says my initial point should be close to M, implicit region. Now, again, I don't know M. How can I initialize my algorithm close to a region that I don't know? Turns out, again, for all of those examples I mentioned, 0 belongs to the implicit region. So remember, in sparse recovery, I want to find a sparse vector. 0 is the sparsest vector. Low-rank matrix recovery, you want to find a low-rank matrix. Matrix of zeros is the sparsest, has the smallest rank, right? For deep neural network, again, under some conditions, I need to be very careful here, right? So that's exactly the reason, in fact, gradient descent, I showed those experiments, gradient descent in small initialization converges, right? This is the reason, because if you initialize close to 0, you're already very close to M. Okay? Now the third condition is the most restrictive. It basically says this relative deviation rate that I mentioned should be very, very small. Should scale with epsilon squared. Now this is very, very restrictive. In practice, sometimes we can verify this is satisfied, but proving is very, very difficult. But turns out, if you have more desirable local geometry, for example, if you satisfy this alpha-beta regularity, you can relax these conditions. For example, you can relax this relative deviation rate from epsilon squared to something that scales polylogarithmically, much better. And the convergence actually improves to almost linear, polylogarithmic, with respect to 1 over epsilon. Okay? Now, I'm not going to talk about this local geometry. But what I'm going to say is that why should we care about this theory? Why does it matter? Seems like we have a lot of conditions. Because it actually gives us a recipe to study implicit regularization for different settings. So there are 3 steps. First, you need to choose your implicit region, as Jeff said. If I am not careful with this choice of M, I may not satisfy those conditions. The second step is to check the conditions. And the third step is to check the relative deviation rate. We actually use this recipe in some of these examples that I mentioned. For example, for sparse recovery, you could essentially recover convergence results that matches with the existing results. Matrix sensing also almost the same, except that we have a worse dependency on R. But our arguments, because we are using this recipe, our argument is much simpler. Instead of 50 pages, proof you only have 10 pages. And for some other problems, matrix completion, we got some results that were not known before. Okay, so if I wanted to summarize my talk in one line, we identified general conditions that enable gradient descent to converge to a second-order stationary point within a low-dimensional implicit region, right? So I think for the next 5 to 10 minutes, I will talk about some of the future work that we are planning to work on. But is there any questions before I move on?
Yeah, okay, other than today I learned that 0 is the sparsest vector, which makes sense. But the theory you just showed, right, is kind of, how do you square that with the random initialization, right? And the fact that usually when you do like the deep neural network training, right, you wouldn't start with 0, right? You'd start with
That's a very
random
good
weights.
That's a very good question. You do not start from 0. Yeah. That's why I said under some conditions. Right?
Okay,
So yeah, no, that's a very good point, because when you're training a neural network, you do not initialize close to 0. But because there are some existing results that basically say that, you know, when you initialize a neural network, when you move around, sometimes you don't move too much, which I think basically means that this implicit region that you want to converge to is already close to your initial. It doesn't have to be 0, but as long as you're close to M, which again you don't know, but as long as you're close to M, this entire, at least together with other conditions, it works. So this condition that I have, the initial point, doesn't mean that you need to initialize close to 0. It just means that your initial point should be close to M. Doesn't have to be 0, right? But yeah.
So it's more that like, whatever those conditions are, it's like with high probability, whatever I'm initializing is close to my choice of M.
Yes.
And then everything, okay,
Yes.
cool, okay, got it, makes sense.
Any other questions? All right. So again, as I mentioned multiple times, all I've talked so far is about gradient descent, right? So the natural question is, can we go beyond gradient descent? For example, can we extend these results to stochastic gradient descent? Now, an immediate idea would be to essentially treat the stochasticity in gradient descent as a kind of a perturbation that would enable me to escape from strict saddle point. Because remember, I needed perturbation to escape from strict saddle point. Maybe I can use stochasticity to act like a perturbation that I need. You can do that, except that perturbations in SGD, they're not infinitesimal. They're not small. And we know what happens if your perturbations are not small. You may deviate too much from n. But at the same time, those perturbations are not isotropic. They're not drawn from a Euclidean ball. You have higher variance in certain directions, right? So in that case, you have structured perturbation, right? But now the question is, can you study this structured perturbation in a way that it's kind of compatible to the general result that we have? Probably yes. We have actually some initial results in low rank matrix recovery, but extension beyond that requires some work. And this is one step that I would say like maybe short term relatively. Another extension would be, can we improve the convergence rate of gradient descent while preserving this implicit regularization? Now, of course, you could say that why not just use, I guess, second order method? You could, but then do you maintain this implicit regularization? That's the key part, right? And in fact, one challenge with gradient descent is that it's actually sensitive to condition number, right? So here, what I'm showing you is the performance of gradient descent on the same low rank matrix recovery. What you see here, this blue curve, when the problem is well conditioned and exactly parameterized, it actually does converge linearly. When you have ill conditioned or over parameterization, you see that the convergence is very, very slow, right? Now, how classical way of to speed up gradient descent is based on preconditioning. In optimization, you have, for example, Newton's method or Gauss-Newton. Both can speed up the algorithm, but the problem is that they fail when either the Jacobian or the Hessian, they're singular, right? And in the over-parameterized setting, you remember, you want to have implicit regularization, which means that you want to converge to a low-dimensional solution. By definition, those low-dimensional solutions, most likely they will have a singular or close to singular Hessian or Jacobian. One other direction is essentially using a regularized version of that, for example, Levenberg-Marquardt type methods. We actually design an algorithm based on that. We call it preconditioned gradient descent or PREC-GD, that at least in this setting, in the setting of low rank matrix recovery, does recover the linear convergence back independent of over-parameterization and ill conditioning. But the problem is that it only works for the analysis only works for low rank matrix recovery. Now the question is, can we go beyond that? Can we extend this kind of regularized preconditioning type methods beyond this specific class? And in fact, we have an ONR grant to investigate this direction. All right. Now the last thing I want to talk about is, can we drop smoothness? Again, I mentioned this a couple of times before. Now, in the smooth setting, we have kind of like a nice, good understanding of the landscape of the problem. In the sense that we know that if the problem is over-parameterized, smooth, and clean, we know that second-order stationary points must be avoided, and they can be avoided. for example, using perturb gradient descent or infinitesimally perturb gradient descent, right? Now, unfortunately, none of these statements actually carry over if you have non-smoothness, if you have noise, okay? In the sense that not all strict saddle points must be avoided, and not all strict saddle points can be avoided. What do I mean by that? Why not? It seems a little bit counterintuitive. Why wouldn't you want to escape from strict saddle points? Now, this is the example that I want to talk about. Same problem, low rank matrix recovery. The only difference here is that instead of using sum of squares, I'm using sum of absolute values, right? So there's no square here, it's just the absolute value. But it's the same problem, I'm minimizing a u d by d. The problem is over-parameterized because the true rank is 3. This u is 20 by 20, right? I'm not left, I don't assume anything about the low rankness. It is non-smooth because I'm using L1 loss. And it is noisy, 10% of the measurements are corrupted with large noise. Here what I'm showing you is the performance of subgradient method, right, on different instances of the problem, and it behaves like this. Now, most of the trajectories actually, so these are for different trials, right? Most of them do converge to M star, right? Now I show this to any optimizer, and I ask, you see that most of these converge. What can you tell me about M star for this problem? It will probably say that maybe it's a local min, right? Local, because you do converge, at least for a lot of iterations, for a lot of trials. Turns out, for this problem, the true solution, this is based on a recent math of OR paper that we wrote with my student John Hao. This is very counterintuitive in the sense that the true solution M star is not a local min, it's not a global min, it's a strict saddle point, meaning that it's a critical point of this function, but it has a negative curvature, okay? Meaning that there is a direction along which you decrease the objective function quadratically. So this solution that I want to recover, this is the best solution I can get, right? This is the true solution, is a strict saddle point. And 2, subgradient method with high probability actually does converge to this M star. So remember the statement I made. I said not all strict saddle points should be avoided because in this case M star is a strict saddle point. I don't want to avoid or escape from that point. And not all strict saddle points can be avoided. This is another evidence. Subgradient method does converge to M star, which is a strict saddle point, right? This is a strange phenomenon that we believe that it actually goes beyond this specific type, like low rank matrix recovery. We actually have some partial results to extend it to. In fact, sparse recovery is much easier than this. But it goes to show that the landscape, the optimization landscape of over-parameterized problems when you have noise and non-smoothness, they're much more complicated than smooth variants. So I would say this would be like a longer term goal to study the landscape of these kinds of problems and maybe also try to extend this implicit regularization phenomenon to beyond smooth problems. And with that, I will conclude my talk and I'll be happy to take questions.
We had a couple questions during the talk. Do you have additional questions for Salar?
So 2 of the examples that you presented, there's kind of a natural convex regularization problem, but then you created this like over-parameterized space and you do gradient descent in that. And you have these, even though that's not convex, you have these nice properties of how gradient descent still converges. But in some sense, one could argue maybe that's not so surprising because there is this convex kind of, like, so the last example is like the neural network. So I'm just curious if that, like, is there some implicit unknown to me or like convex problem that's somehow behind the scenes there? Or
maybe
is that somehow
there are some results that that basically show that like there is some hidden convexity in some classes of neural networks, but I'm not sure if it's like extremely well studied. And for example, like if you were, I don't know, there are some, if you have this, some work they like they under some conditions you can say like you can approximate locally a neural network can work like a kernel regression type problem, and that is a convex problem. So to some extent, yes, but I wouldn't say it's as general as, for example, sparse recovery or low-rank matrix recovery. One thing I should mention though, for both of those problems, we cannot argue that they're completely independent of the unknown parameters, because, so in other words, convex relaxation, for example, for low-rank matrix recovery, go all the way back. Yeah, convex relaxation for low-rank matrix recovery still needs, technically it still needs some information about the rank, because this, there is a lambda over there as well. You need to tune that, right? And again, that does depend on the true solution that you don't know. So yeah, I mean, that's I think one of the main reasons that we also want to look at these non-convex formulation, and on top of that, I mean, these tend to be much simpler and smaller scale.
Questions? I have a quick question, more just about, so is this now, I don't really, this isn't my area, but is this now the state-of-the-art way to solve these, instead of using like solving the optimization problem that is the regularized version, used to over-parameterize and run gradient descent? Is that how they do it in practice, because it has these convergence properties, or are they still solving the other?
No, I don't think the reason why we solve over-parameterized, I mean, sometimes yes, but I don't think it's, the main reason isn't because there is this nice property. In fact, it's the opposite. Like, the reason why we started working on this is because people kept using it in practice long enough for us to see this.
Just using the
Yeah,
over-parameterization
yeah,
and running gradient
yeah.
descent. So that is how they kind of do it.
Yeah,
Okay.
yeah. In a lot of, of course, I mean, again, it doesn't apply everywhere. I mean, you do have, sometimes you do want to add regularization for different reasons. Sometimes you do know the rank. But yeah, I think.
So you have a question?
Yeah, I have a practical question. So I think those theoretical results nicely explain some of the guidelines we received when we train the network or train the over-parameterized
Yeah.
the machine learning model. For example, so we know you initiate the network with small values. Yeah. So based on your results, do you have other guideline, like other surprising thing you can suggest when we train a large network? Like how to quickly get the result we want?
Yeah, so one thing that I should mention is that when we talk about this implicit regularization, for example, low-rank matrix recovery, right? So for this problem, when I run gradient descent, right? I don't know the rank, but along the way you can kind of guess the rank, right? Because so you have this matrix that is initialized close to zero, and it changes over time. Like you run your algorithm, it does converge to something, and you can see that this low rankness emerges over time. Which means that at some point you could guess the rank, and if I guess the rank, I could essentially limit this U, instead of D by D matrix, I can limit it to be D by R. Because then R is the approximate rank that I see in my current solution. So that is something that you can use. Basically gives you some hint on what is the actual dimension of the problem. That's one thing. The second thing is, it does help when you want to design preconditioners, when you want to speed up the algorithm. Because if you know that you're close, if you get a sense of what your implicit region looks like, you can design a preconditioner that works really well in this implicit region, but not necessarily outside. Does that make sense? So it does give you some sense of, you know, how to design the algorithm and how to speed it up.
Okay, I think we're at our time. We have a lunch date, but let's thank Salar for a very interesting, fascinating.
Oh, thank you, thank you.
Hey, I have to run because I have my own lunch date.
All right,
I'll catch you
I'll
up
see you.
at my office later,
Yeah,
okay?
of course.
I will pick up.
Sure, sure.
Not this one, not the first one.
I saw you last year's. I see you.
Oh, yeah. I was on Zoom, right?
Yeah.
Yeah, it's like 2 seconds.
I try to bring.
Wow, nice.
Ellie requested that, and then I was like, no, I'm
Is it like
checking
in the,
my
is it in the
Uh-huh,
upper room or in the lower floor?
I mean, you don't get reserved, so basically,
If the schools,
guests are just like, what
you will finally escape this
Yeah. Oh, that's
critical
cool.
this set of points.
The first time we like gathering.
We always follow.
Yeah, right. Yeah. We were still stuck with
How
like
is
It's very,
like in the marketing.
Yeah.
yeah, I mean,
Wow.
in the non-school setting, it's very difficult. Even the definition of sticks out depends.
February.
There's this notion of active and inactive.
I found it like that I
Turns
have
out
to
you can skip from active strict
Yeah,
sets
yeah.
from non.
because otherwise, like,
Yeah.
It really depends on
Yeah.
the type of strict saddle point that they deal with in the non-school setting, which is the reason
So,
why the
yeah, I was
problem
like,
is.
Oh, sorry, you said for some reason I was thinking about the library, not the children's museum.
They have
Oh, I think I need to
an
reset
paper
before I
that
go
shows
to
that essentially
the
they're
library. I tell them when
we've all
we
been there. I
Yeah.
Want to leave it right here or anything, or you can?
I don't, can I
Yeah.
leave it here?
Yeah, you can put it in the office.
Okay, okay.
Well, do you want
Okay.
me to be
Free.
have lunch.
Can I when are you going back to
After office
Perfect.
hours.
See you later.
Yeah, see you later.
Let me see.
Office hours?
Yeah, right after
go to
our
the
lunch.
lunch hour?
I can take it now. Thanks for coming in.
See you, yeah.
Good to see you
He's
too.
trying
You're freezing, like your hands
I'm always cold. That's why
to-
I'm
It is very
always
cold in this room.
very
I don't know
close.
what's going on.
I have like constantly a low blood pressure.
Really?
Like
I guess
even
that's-
when I'm not like
Yes, that's, it could be, yeah, low blood pressure, I guess, is better than high blood pressure, like from a
Yeah.
health perspective, but you don't want it to be too low, right?
yeah.
Yeah, no, I was about to say, I expected you to have acclimated even to cold
No,
weather.
trust me, I am. But yeah, it's I'm naturally like my hands are cold. How are you?
Okay.
How are things?
And I'm just like constantly feeling sleepy. I think it's like the winter
Cold is
sleepiness.
the dark.
Yeah.
Yeah, I sort of feel that.
Yeah.
Thank you all.
I should probably
Back
hand
here,
this.
Oh, yeah, I'll take
He's
that.
not a thief.
Not a thief, we'll note that on the,
Yeah, note that on his survey form.
yeah, exactly. And then you'll bring him to the dean?
Yeah, I'll take him to the dean, but
Perfect.
unfortunately I have a.
Yeah,
three, so
I think
can't
the dean is
hang
gonna
around.
pick him
Okay,
up, so,
thanks.
yeah.